Did that work?
It should have worked. I got a thing in the corner that said that he's the host now.
Yeah, I'm the host. I just lost the picture. Yeah, okay, so I am host now. I have a second screen, which it's inexplicably not working at the moment. I don't particularly need it, although I was going to take all of your faces and put it on the second screen. I'm sorry. I thought things were going to go a little smoother, but I should have known better. All right, so we're going to be talking about chapters 1. There's not a lot to talk about in chapter 1. And then also chapter 2, and maybe get into 3 today. So when I share this screen, all right, I got you guys in the corner, which is not where I want you. Let me move a couple of things around here. That's my, okay, I put that there. No, not my whiteboard. Sorry, just shared the wrong screen. There we go. Okay. We're good. We're good. It'll go more smoothly on Monday, I promise. That is right up until the time I find my pen. Okay. And my correct page of notes. All right. We all here? More or less?
Physically, maybe mentally is a little bit questionable. But.
Yeah.
Well, I'm the only one that matters, so yeah, I'm here.
All right, and you're seeing the screen, right? The white screen?
Correct.
That I'm moving right now? Okay. Just got a new computer. I was doing this off of a pad before, which was a little bit of a different feel. So it might just take me a little bit to kind of get used to this, but for the most part, we should be good from here on out. Okay, so chapter 1, really simple, X, Y axis, related, unrelated, directly related, inversely related. We'll talk about those. I wrote out the 10 to the 9th to the 10th to the negative 9th chart, just because that's kind of important for us to know. We're dealing with really large and really small numbers, and to kind of understand what that means, and then also to be able to look at it in an equation and realize that sometimes a very large and a very small number will cancel each other out perfectly. So,
Are we supposed to be looking at something on the screen?
You see that?
Yes.
Okay, good. So, not yet. So, we have some different values or different ways of talking about things, and this is really basic. I understand that, but unrelated. Unrelated just simply means that if you change a value, it has absolutely no effect on another value. Pretty straightforward. I'm not going to write anything else down for that. Then we have related or proportional. And that really refers to something that if you affect one value, it affects another value, of course. So I try to keep things as simple as possible. So if related or proportional could mean, like, if I put one value up, the other value might go up as well. It might go up to a greater extent. It might go up to the same extent. It might go up to lesser extent. But that's one form of relations, is that you affect something and it affects another thing. The other possibility is that I move a value up and another value goes down. So if I turn up my power, my volume goes up. That would be an up, up. Whereas if I turn up my, I can't think of an example now in ultrasound, but you have opposite relations or both of them doing the same thing, going up, or one going up, one going down. Inversely related. Now this doesn't related or proportional, just simply says that there is a relation, but it doesn't really tell you too much beyond that, like what kind of relation. Inversely related or inversely proportional always means the second value. So the second example. So if I go up with one thing, I go down with the other thing. So no matter what we're talking about, whatever value this first value is, it has an inverse relationship or an inverse proportional relationship with the other value. The other value always goes down.
What's your room, please? Because I need to pay attention. I'm so sorry.
No, that's okay. With this, I have a different format that I'm used to. I'm looking for the mute everyone. But that's okay. No worries about that at all. Now, once again, on this inversely related or inversely proportional, we're saying it's only in this way. One value goes up, the other value goes down. One value can go up a certain percentage. The other value can be much greater going down, or vice versa. So these don't have to be equal. Equals are a special type of inverse. A special, can you guys still hear me all right? I know I'm talking a little loud. I just got shut because my daughter's taking classes too. A special kind of inverse relationship is reciprocal. A reciprocal relationship. In that case, it's similar to this one over here, except it's always equal. One goes up, the other goes down. And whatever this is, when you multiply these two values together, they're going to equal 1. Now we'll get more into this. We'll throw some numbers into this later when we actually do some actual math involved. But I just wanted to go over that part. Does that all make sense so far? Anyone? Any issues? Okay.
I wish you would have taught us last semester, because this helps a lot.
Oh, okay, good. All right. Feedback is good, even bad feedback. If I am not clear, or if I'm, let me know. Okay, so this one I wrote out ahead of time because it obviously made sense to do that. So hopefully you guys understand 10 to the 9th is really just meaning 10 times 10 times 10 times 10 times 10 until, so you get 9 zeros. So 10 to the 9th is 9 zeros. That happens to be a billion, also known as a giga or large G. So 9 zeros for 10 to the 9th. We don't use this one too much. This one, 10 to the 6, or 1 times 10 to the 6 is mega. A large M, or capital M, and that's a million. That's the same thing as saying 1, 2, 3, 4, 5, 6. 6 zeros. And then there's 1,000 is a kilo. That's 10 to the 3rd is 1,000 for 1 kilo, and that's of course 1, 2, 3. 10 to the 2nd is 100, 10, and then we have a 10th, 0.1, a 100th, 0.01. That's correct, right? Yeah. Thousands, 0.001. Notice that it's not 0001, it's 001 is a thousands, because you count decimal points 1, 2, 3. Okay? 10 to the minus 6, this is another one we use a lot. A millionth is a micro, and this guy is a funny looking letter U. It's not just a U, well, it's not just the letter U, it is a U shaped like that. And it's Greek, and I cannot remember for the life of me right now the actual pronunciation of that term, but that's okay. We're going to call it micro anyway. So that is the symbol for micro, and that is 1 million. So 0.123. That's right. We went from 3 to 6. I'm like, wait a minute. 1, 2, 3, 4, 5, 6. It's not 6 zeros. It's actually 5 zeros plus the 1. That makes the 6 decimal points. So the minus 6 is for 6. And then we have nano. Actually, we use nanos quite a bit as well. So that is a billionth. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 to the minus 9th is a nano, and that is basically just a small n for that.
I just want to point out real quick, when answering questions in the homework and stuff, to be careful with the capitalization of the lowercase m and the capital M, because I got a few questions wrong in the homework because of that.
Good point. Yeah, capital M, small m. Good point. And then it's for kilo, for some reason, it's a small k, small h, duh, small d, small c on those. Yeah, it's a good point. The other thing, we'll once again, when we start doing some of these equations, using some of these numbers, it's going to look intimidating at first, and it's really not going to be that intimidating. We're going to make this as straightforward as possible, because you're not expected to be mathematicians. God knows I'm not. But I will say, it's kind of an interesting thing. When we use a mega, a million, let's say that's on the numerator of a fraction. We're working out a fraction, and on the denominator, we find a micro. Interestingly enough, and mathematically, I actually find this very curious. These guys cancel out. So a million, and I believe in your book, I should open the book too. it does read on page 6 of your book. They're calling them complementary metric units. So the gigas and the nanos are complementary. The mega and the micro, which is what I indicated here, are complementary. And so they will cancel each other out. In any case, it's a good idea to know those, especially the micros, the nanos, and the megas, but we'll also know some others. Okay. Oh, and so I have a question for you guys. It's not really, this isn't a, get both my, well, if I don't want you here, there you go. I wrote too big on my screen. That's okay. I could erase everything. Let me just check something. This I set this up to automatically record. It is recording. Okay, good. Okay, here's a question for you guys. What is sound?
Things you hear?
So what is sound? Anyone?
It's a wave, a disturbance of the molecules within the wave.
That's a good answer. It's a wave of a disturbance in the force. No, it is a wave of sound. It's a wave. It's a wave in the molecules. It's a pressure wave. Actually, boy, that explosion in Beirut, that unbelievable explosion, that was a pressure wave. That was sound, really. And producing an ungodly amount of damage. That actually is, in a sense, it is sound.
Rapid heating up of the particles and molecules.
Yeah, now if a tree falls in the forest and there's no one there to hear it, does it make a sound? Yes or no?
Schrodinger's cat, alive or dead?
Schrodinger, it is both. That's actually a good answer. Schrodinger's cat is neither alive nor dead until you observe it. And the sound, it depends on how we define it. As you defined it a minute ago with a disturbance in the molecules, then yes, a sound is created if no one is there to hear it. But when we think of sound, we're thinking of something we hear. It's actually, our brain is interpreting movements in the air. So regular rhythmic wave movements in the air is sound. So if a tree falls in the forest and there's no one there to hear, no one there to hear it, in one sense, there is no sound because there's no brain to interpret it. But in the other sense, there is motion. At least we think there is, according to Schrodinger. Oh, and then how does this? This is a movie from a long time ago. There's a quote from a movie here. It says,
Isn't that from Aliens?
I think so. I never. It might be aliens. I'm not sure. But in space, nobody can hear it. What's that? What's that word there? I think I heard you say it.
He's gonna scream.
Scream.
No one can hear you scream. Why is that? Why can't, if you're in space, no one can hear you scream. All those Star Wars movies are things explode and you hear the explosions and you hear the laser, the phasers or whatever they are. We actually don't hear anything in space. Why is that?
Sound can't travel through a vacuum.
Yes. So sound needs a medium.
There's a bunch of nerds in here, huh?
Water, tissue, et cetera, et cetera, et cetera. Sound needs a medium to travel through. So you're right, if it's a vacuum, and I have had students, I say vacuum and they think Hoover. No, that's not quite it.
Isn't Hoover the dam?
Yes, true. All right, Dyson. Yeah, it needs a medium. Unlike electromagnetic, and I only mention this because some crazy reason, sometimes they'll ask questions on this. Electromagnetic does not. Those are waves as well. But they do not need a medium. What is electromagnetic?
No idea.
Magnetic forces created by an electronic or an electrical power.
Well, it kind of is. This is ultrasound. We really don't need to get into this. We literally just need to mention it. It actually is important to mention because sometimes the SPI will ask as a reference. Electromagnetic is light. If you notice sunlight, and I think most of us know light is a wave, particle wave, wavicle, but it's a wave. But it easily travels through a vacuum. It does not need a medium. Electromagnetic is light. It is, radio waves are a form of light. Infrared light is light, or infrared radiation is light. It's just beyond our ability to see, but we certainly feel it. That's what you feel when you go out into the sun. You actually get the infrared heat is getting you. So that's electromagnetic. That's actually, and you're right about that. The magnetic causing an electro, or an electro causing a magnetic. This is electromagnetic. You know what? Let me draw this really quickly, and then we're out of it, because I don't want to. Obviously, for obvious reasons, we don't want to spend too much time on electromagnetic. Doesn't make sense. But let's see. I'm going to draw a wave like this. This is really hard to draw, so. And then I'm going to draw another wave. Actually, here, I'm going to draw a baseline here so that we're. That's just a baseline. And let me get this screen back. Let's see. No. Don't want you. I don't want you. Don't want you. There we go. You don't have to draw this. Let me just shade something in a little bit here. Shade. I'm trying to draw a three-dimensional. Okay, that's my attempt at a three-dimensional aspect of a wave that's traveling in both kind of up and down and side to side. And electromagnetic is you're correct. There is an electrical force causing a magnetic reaction, and then a magnetic reaction causing an electrical force. This is what light is. Whoops. Light is a EM wave. Self-propagating, the electric force causes a magnetic force, the magnetic force causes an electric force, and it goes on forever. And light will travel through space forever until it hits something. Done with electromagnetics. We don't need to talk about that anymore. It's crazy that we have to talk about it at all. But just that it does not need a medium, whereas our waves have to have something to travel through. Why? Because they are our waves, our sound waves are mechanical waves. Okay. All right. Getting used to this program. Actually, I'm used to the program. What I'm not used to is using this particular computer. It's very different. All right, let me just, I need to get a lot more width. And let's get a lot more height as well. I'll go full 9,000 on that too. Okay. Oh, dummy. All right, guys. Well, you know what? It's just actually easier. It's recording, so if you missed anything, I will have this on YouTube. I'll give you the channel as soon as I have the channel. Okay. Actually, no, I need to be in closer. Okay. Now I can start again. So sound is mechanical. What is a mechanic? A machine. Mechanics work on machines. Mechanical is machine-like. And so when they say mechanical when it comes to sound, what they're really saying is that it's a physical action rather than electromagnetic waves, which are more magical. This is a physical reaction. That's why a medium is needed. So when we think of sound, oh, go away. You need to go away now. You need to. There we go. Okay. You know what? Let me just pull this down a little bit so it's not always disappearing on me. All right, let me just put a baseline in here. That's just, that always represents 0. Whatever it is, 0 centimeters, 0 velocity, 0, anyway, baseline is always 0. And we think of how we draw these. Let's do a nice pretty color again. Blue. Okay. We think of sound waves like this. Basically, we think of it as waves on a water surface. And then a lot of times when we're showing examples of sound waves, we'll throw a rock into a pond and you see the supposed sound waves traveling away. And think about what that looks like. It actually travels pretty slowly. You can easily watch the wave travel away from where that rock was. That's not what sound is. Now, we use this representation all the time. The reason we do that is because this is easy to measure. It's easy to measure that value, or my handwriting's become suddenly very messy, and I understand why. I've made my pixels. I've have so many pixels in here that it's not working out. That's okay. Live and learn. But anyways, we use this format, and we're going to be using this format throughout the semester to measure waves. We measure the amplitude of a wave here. Okay, yeah, I have to fix that. We measure the amplitude of a wave here. We measure the wave length, which is represented by this guy. It's lambda, from here to here, about there. It's just easy to do, because what a wave actually is, sorry guys, I have to change the canvas size, because if I don't, sorry. Okay. What color am I? Blue. All right, so this is called, technically speaking, a transverse wave. Sound is not a transverse wave. We draw it this way simply because it is so much easier to deal with. I'll finish talking about transverse waves right now. A real transverse wave, a wave on the ocean, or a wave in the pond after you've thrown a rock into it, each particle, let's say that's a bobber. You have a fishing bobber in the pond, and some jerk throws a rock in, which makes pretty certain you're not going to catch a fish. But what that bobber does, as the waves go by, it goes up and down. And it could be at the peak, going, well, it doesn't have much more up to go, and up and down. It could be at the trough, or the lowest point, and goes up and down. In any case, particles are traveling up and down. We don't have transverse waves when it comes to sound. We have, they're mechanical and longitudinal. That's a big difference. Anyone know how fast tsunamis or tidal waves, when they're still out in the ocean, traveling across the ocean, anyone know how fast they go, approximately?
Very fast.
They
Over
are
250 miles per hour.
Yeah, easily over 250. They travel about as fast as an airliner, like a 747. Transverse waves never travel that fast, thank God. Or they were going to the beach would be hellacious. But mechanical longitudinal waves do travel that fast. Mechanical longitudinal, let's see if this works. Oh. Let me draw it up here. Didn't leave myself a lot of room. Different color too. Let's go back to green. Mechanical longitudinal. Let's draw. So the dots here, and I'm so happy I found this particular pen, or this particular, represent compressions. And then there are other parts. You know what, I'm not going to use that. Oh, I'll just do this. Okay. Color, please, on the color. Red, it's fine. Okay. So this represents a compression. And exactly what it sounds like, it means that's the part of the wave, the sound wave, where everything is together. Every molecule is closer together than they normally would be. I'll choose over here. This represents a rarefaction. Sorry guys, but I need you out of the way. Sorry. This represents a rarefaction. Rarefaction. So rare as in it's Mongolian mongooses are rare in El Paso. I would hope anyway. So there's not a lot. Now notice that I lined it up with the transverse wave above. So a compression on the transverse wave, or at least the transverse wave representation of our mechanical wave. Does that make sense? This is what the wave actually is. Let's put a check mark here. This is what the wave actually is not, but this is the way we are going to be drawing it all semester long because this is way too difficult. Like how would you measure amplitude by this representation? Very difficult to do. So anyways, this too is the compression. So it's the peak. We'll also call this a peak. It represents the compression, the part of the wave where everything is squeezed together. And then, I'm gonna throw my baseline in. Let's just kind of put a baseline like right about. Okay. Remember the baseline always represents 0. So if there was no wave at all, it would only be a baseline. The baseline also represents the average between the peak and the trough, like a horse trough. Or, that's not a good word. Anyway, peak and trough, or highest compression versus the lowest rarefaction. So rarefaction is also represented here, right there, kind of. No, go. Right. So mechanical longitudinal, mechanical compression rarefactions, electromagnetic is not. We already talked about that. Okay, so there's also a couple of assumptions in ultrasound. The book at this point doesn't yet mention assumptions, but that's really what they're talking about. We assume that sound travels in let's help myself, in a straight line. And it does. Sound actually does travel in a straight line. The problem is that we have a hard time imagining sound traveling in a straight line when we know that when we throw that, well, when we look at the explosion of the, in Beirut, we see it going off in all directions. We see it expanding. We see it, there's a circular wave front. So all those things kind of in our brain tells us, well, sound travels, it doesn't travel straight, it travels out in all directions. When I'm talking at one person in the classroom, when I'm aiming at one person in the classroom, it doesn't mean they're the only person who hears me. It might be the only person paying attention, but they're not the only person who hears me. Everyone in the classroom hears me. So our brains want to say, well, no, sound doesn't. It does. Sound travels in a straight line. It just happens to be traveling in all directions in a straight line. Now that's an assumption. And the reason why we say it's an assumption is that in ultrasound, we actually do create a narrow beam of sound. And so if we go back to this red arrow that I just drew here, we can kind of imagine that as being a narrow beam of sound. And so in that case, yeah, it travels in a straight line. It is a laser beam of sound that we use. It's an assumption because unfortunately that laser beam is hitting things all the way down the line, so that instead of going straight, it's going a little bit off this direction and then back this direction and this direction and this direction, and it's bouncing back in different directions. But hopefully some amount of that sound, some amount of that sound comes back to us, but it's an assumption that sound always travels in a straight line. It's a correct assumption. In our case, we deal with a lot of echoes, so it's an assumption that doesn't always work. Okay, in my notes, I said I am skipping page 12 for the moment. And I forgot why. What is page 12? Acoustic variables, acoustic parameters. I've already done it. Actually, there's one thing, good thing I write notes down because there's one thing I did forget to mention. Up here, I told you how any one particle in a transverse wave is going up and down, like a bobber in the water or a boat on the ocean, goes up and down. On a mechanical longitudinal, in other words, sound, each individual particle, let's make it this one right here, is going back and forth. Or these particles in here are going back and forth or forth and back, whatever.
So I have a
That's
question.
me.
I'm not sure if this is a dumb question, but still, is it safe to say that sound only travels perpendicular?
No. So what do you mean by perpendicular?
I don't know. I put it down one of my notes, unless I'm confusing it with the transverse waves that travel perpendicular.
That was probably page 12. So I'm in chapter 2 now, aren't I? Okay. No, here, transverse waves partly move in the direction that is perpendicular at right angles to the direction of the wave. Okay, I know what they're saying. Here, let me, bye-bye. I know what they're saying. Let's get rid of, Control Z is supposed to get rid of all the last things that I did, and of course it's not, so let me just erase some. No worries, hon.
You're better than me. I would be having like a piece of scratch paper holding it up to the video screen.
So the direction of this wave, let's just say it's going from left to right. The direction of the wave is there. The particles are perpendicular to that. Whereas down here in the mechanical longitudinal, the direction is that direction, and the particles themselves are going both with that direction and then backwards as well. How do they say it? Move. In longitudinal wave, particles move in the same direction that the wave propagates. Yeah. Same direction, and then also the opposite direction, because they're vibrating back and forth like this, whereas a transverse wave, they're just, it actually, if you could see an individual particle, even though the wave's traveling, going across this way, the individual particles are simply going up and down like that. That's what that means there.
Got it.
Okay. So actually now I am back to page 12. I'm going to have to do a big fat erase, I think, because let's see how much room I have. Yeah. $11 Okay, normally I would build a break in. I'll do that next time. So, of course, I could skip breaks and then we have a shorter time. Well, no, I'll put a break in because sometimes I need a break too. So it's not about you guys; it's about me. No. Honestly. There we go. That is one function I am not a big fan of here. Let's see, black lettering and a little helper. Okay. So there are variables and parameters.
Seven.
Acoustic variables. Those are pressure. So in our case, pressure is going to be strongly related to the power or the volume or the amplitude. Pressure is in the units of pascals. I'm just going to put PA here for pascals. Density. Pressure and density are going to be related. They're directly related. Pressure goes up, the density goes up, at least in the compression part of the wave. So that could be in kilograms per centimeter cubed. Sometimes also just denoted as P for pressure. I'm sorry, P for pressure. It is a P. It's this one. I remember this one. It's called rho. It's a funny looking P. Okay. So pressure, density, distance. This too is related. Now, they, I think, are, you know, it's centimeters, feet, miles, whatever. We're dealing in much smaller numbers, but I'll just go ahead and put like, say like millimeters, centimeters down. But we're dealing with much smaller actions in that. When we say distance, and as far as acoustic variable is concerned, when we say distance, we're talking about that particle and how far it travels back and forth. That is directly related to the pressure and the density. These are all really directly related to each other. When we draw a wave like this, what we're really saying, when we're saying how far it travels in one direction or the other direction, well, really it's traveling back and forth the same amount because it's just vibrating. What we're really talking about is the amplitude, which is something we're going to measure right here. Amplitude is basically the volume, and volume is pressure, so they're all related here. Okay, I think I'm just going to have to do a big fat erase here and go back to darker. Black is not very black. I want jet black. There we go. Okay. Dang it. There's another setting somewhere in here that's making everything a little washed out. That's all right. Does not matter. Acoustic parameters. These are the things we're going to beat. These are the things we're going to measure, really, when we're...
It's the type of pen you're using.
You think?
You're using the highlighter pen.
No. No. No, this is my chisel tip. This is the one that kind of makes, for some reason, it makes me write a little bit cleaner. I'm not the best penmanship, but anyway, so acoustic parameters. So I'm going to go ahead and draw a little wave in there. We're going to talk and just put a baseline in. So we can, okay. I need to make this a little smaller so I can fit. Okay. Period. Number one. Period. Period is a time function. So we're just going to put a small t here. For us, period is going to be oftentimes measured in microseconds. Frequency. That is usually kind of a fancy looking F for frequency. That is going to be measured usually in the mega, capital M, hertz. Hertz is something how many times, usually in a second. It doesn't have to be seconds, but that's what it usually refers to. Megahertz is millions of times per second. Frequency amplitude, I mentioned that. What is the amplitude going to be in? Usually denoted by a capital A. Amplitude is going to be in watts, but amplitude is basically when we measure that here, from here to here, baseline to peak is going to be our amplitude, how strong the wave is. Well, let me go back. Period. Well, from the beginning of one wave to the beginning of the next. A wave is not only the part that, I'm doing this as if you could see my hand. It's not only the first part, but it's the second part. So not only, give me, oh, okay. Not only here, that's only half of a wave. Here's the whole wave. So we measure from here to here for the period, and that is, of course, time. But we're also going to measure there, we're going to measure from there to there for something else as well. We'll get to that. Frequency is the number of times that this occurs in a given amount of time. Now, once again, usually in a second. So if this point, let me erase a little bit so that, oh, jeez. Got a giant eraser right now. There we go. If frequency, if we call this from here to here, if we call this whole space 1 second, what's our frequency? If this is 1 second, what's our frequency?
2.
2, exactly. 1, 2. And so we could count peaks, but it needs to be, the peak in the rarefaction is 1 full cycle. And let's define that. Period is the time we measure from here to here. How much time did that take? Usually a millionth of a second or less in our case. This is also 1 cycle. Happens to be from that point to that point. We don't talk about cycles just yet anyway, so amplitude, frequency, period. Okay, we got those. Let's go back to my thinking. All right. Amplitude, what's the next one? Power. Power, P, it's usually like in watts, but power and amplitude are very closely related. You turn the power up, the amplitude goes up. You turn the power down, the amplitude goes down. Intensity is the next one. Intensity is also related to power, but it's a slightly different relation. Power goes up, intensity goes up. Power goes up, down, intensity goes down. So it's still a direct relation, but intensity is power per area. So if I can keep the power the same and change the intensity, just like a flashlight. If I could take a flashlight, I could dial it out so that it covers an entire wall. It's the same amount of power. Same amount of power, I'm covering the entire wall as when I narrow that beam down to a small point on the wall. Let's say I have a really high quality flashlight and I'm able to make like a sharp beam. Power has not changed. The overall power has not changed. However, the intensity at that point has gone way up because now we're sharing, instead of sharing that power throughout the entire wall, all the power is focused on one point. So that's what we talk about with intensity. Wave length is denoted by this guy, lambda. So I said before, when we measure one cycle, we're measuring the period. Well, that's if we measure the time that it takes for that cycle to go past. But if we're only measuring, or if we're going to measure the length of that cycle, that's the wavelength, and it's the same place. So let me just put a little focus right there. Wavelength. So basically, from here to here can be wavelength, it can be period, and it's always considered one cycle. And then our last acoustic parameter is propagation speed. That is denoted by a small c, not copyright, but a small c. It actually stands for constant. And it really comes from the speed of light is actually small c as well. So if you were a physicist working out E equals mc squared, c is the constant speed of light. For us, c is the propagation speed. We assume it's constant, but it's not. Okay. Good so far, everyone? Anyone panicking yet, or?
I'm always in a panic.
Just a little bit.
Just a little bit. All right. Well, remember, I am always open for. I have students from my other class are contacting me and asking questions. I train them. Well, there's only very few of them who do it, but they'll ask me questions, and then I answer them right then and there, and then I probably will remember to bring it to the entire class's attention. And then I totally gaslight them. I'm like, well, Brianna asked it. Okay, page 14. This is fun stuff. This is, let's see. Let's make sure we're good. Yeah. Page 14, time is 11:22. We started at 10, okay. In phase and out of phase waves. Let's do some pretty colors here. We're gonna do, I'm gonna use a little trick I learned the other day here. Where's my, no, I don't want, okay, here we go. There's a little cheater trick I just discovered, which is so awesome. Okay, let's get you going too. Actually, no, little cheats. Which is awesome, but I wish I'd drawn that second. I hate chihuahuas. Okay. So I wish I had done the green on top and the red on bottom. That's okay, no worries. So starting with the green, these are two separate waves. They're kind of in sync, right? They're in phase. And if they happen to be in the same place at the same time, in other words, two waves traveling through the body or through the air, through the water, it doesn't really matter. And they just happen, not only are they traveling so that each peak is lined up and each trough is lined up, but they're actually on top of each other. What ends out happening, I didn't leave myself a lot of room here. Did I leave any room for myself? I did, okay, there's a little room here. What ends out happening is you get one larger wave in this case, of the same frequency, because these two were, as I drew them, they're those same frequency waves in phase, in the same place at the same time. They constructively interfere and whatever. Doesn't matter, I can't spell. Constructive interference. And if you guys have ever heard of, there are such things out in the ocean called rogue waves. And they'll just be sailing along, and then suddenly a 50-foot wave comes out of nowhere, and a lot of boats have been lost without a trace, not without even so much of a distress signal. Rogue waves, they're really scary. And what they are is, in certain places in the ocean, with certain winds creating the waves, sometimes these waves just happen to line up perfectly and they create massive waves. And these things they could travel a very long distance. So you're not even in the storm and suddenly you get hit by a 50-foot wave. Pretty scary. I don't go to the ocean very often. So that's constructive interference. And it happens in ultrasound as well. We can constructively interfere our sound waves. Destructive interference, hello, is just the opposite. Two waves traveling at the same location, except now their peaks and the peak and the trough line up, and the trough and the peak line up. I almost said that wrong, because this is a peak.
So it makes them out of phase.
Trough, did I say trough? Yeah, I think so. Peak, trough, trough, peak. When those line up, and if they line up perfectly, you get no sound at all. This is destructive interference. If anyone has sound canceling headphones, this is what's happening. The electronics in those sound canceling headphones are amazing. And what they do is they actually hear outside noise. And as that outside noise hits the outside of the headphone, it listens to that and creates an equal but opposite wave and sends it out. And those two waves, those sound waves, match up, but they match up perfectly destructive. And if you ever worn a good pair of those, they're pretty amazing how well they work. And there's one other. So this happens all the time in ultrasound. I don't want to get into it. Don't want to mess with your brains just so much yet. There was one more that they showed where, let me use my little cheater again here. There was one where the resultant wave, let's use a different color. So, first we have constructive interference where the wave is larger than the original wave. And by the way, these don't have to be, this wave and this wave don't have to be the same amplitude. I could have made one of them larger, one of them smaller. They will still constructively interfere. These two, to make absolutely no sound, they have to be perfectly the same strength, the same frequency. But so far I've drawn both with same frequency. Let's say 1, 2, 3, 4, 1, 2, 3. Let's say that they're both 4 megahertz, we'll just pretend. They showed on the book a resultant wave. Now I want to say resultant is this is the result of these two waves, and this is the result of these two waves here. The resultant wave they showed, let's see if I can do this right. Yeah, and then they just kind of filled it in, I think. Okay. Hello, where's, oh, I don't want middle, okay, good, all right. There we go. This, they didn't use this term in the book. What term did they use? they didn't give it a term at all. They just simply said both constructive and destructive interference. This is, it's actually called a beat frequency. And what happens here is that we have two waves. One, whatever frequency that is, and then the other, let's use a different color, a different frequency. Well, these two waves, just like the other ones where we had perfect constructive interference and perfect destructive interference, this is a little more realistic because life isn't perfect. We're usually not dealing with very precise frequencies. We're dealing with multiple frequencies. And as you could see, sometimes a trough lines up with a peak. So this is a trough up here, and this is a peak down here. At other times, yes, good. A peak lines up with a peak. So we got a peak and a peak. So over time, what ends up happening is that you have temporarily constructive interference. It makes the waveform have higher amplitude. And then sometimes you have destructive interference. The amplitude goes down. Now, I didn't make these perfectly destructive, but I suppose I could have. So just as a reminder, let's see. Constructive interference, that is this one, right? Peak, a peak, and a peak lined up. It created a higher amplitude. We measure amplitude from the baseline. I'll just quickly throw a baseline in there. From the baseline to the top, to the peak is a amplitude. Technically, you could measure amplitude down here too. We just don't do it that way. And our destructive interference was this one, a trough. What happened? Oh, I'm still in.
I have a question.
Mm-hmm.
So, because I'm following the book at the same time. So construction interference, the amplitude is bigger. Destructive, the amplitude is minimal. But
Yep.
There's another form of destructive where it's complete destructive, where it's absolutely no sound, no amplitude at all. Am I right?
Yeah, so it's pretty rare that you have perfect destruction of sound. Because there's always, well, first of all, this occurs almost all the time where sound waves are of a different frequency. The other thing that I didn't really draw up here, both of these on the constructive and the destructive, I made the amplitude equal. If on my destructive interference, actually, let's just go ahead. Get rid of all that. Let's say I drew that, and then I want to do an interference pattern. So my next one's going to be, let me just, my opposite is going to be like this. Oh, for God's sakes, Kurt. All right, for some reason I can't seem to draw it. Let's just try it again. Whatever, okay. Let's say my amplitude here, I'm just gonna make up a number, is 3. But the amplitude on this one, going the opposite direction, is 6, it's double. The resultant from these, let's say in every other way, they were lined up, the peaks and the troughs were lined up such as that it creates destructive interference. If the amplitude of one and the amplitude of the other is not the same, then you can't possibly create no sound. There's still going to be sound because the amplitude of this wave is such that you end out having a wave that's smaller with a smaller a smaller amplitude. Let's say if these crossed out perfectly, I don't know if they would, you would end up with an amplitude of like 3. And these are completely made up numbers. It's actually surprisingly hard to draw that. Does that make sense though? It rarely happens that you get perfect destructive interference, but it can happen. Like if you have a really good pair of Bose headphones, I guess.
Yeah, like if I muted you right now.
If you muted, yes. If I'm muted, then that would be an example of perfect. Wow, that. Okay. 1137. Yeah, I would say that the next chapter is actually, so the next chapter is pretty big compared to this. And we're going to get into a lot of measurements of the wave. You know, measuring here, measuring from here to here, measuring, what else? Intensity, wavelength, some equations. Oh, fun. Now we're doing propagation speeds. Yeah, that's a big class next time. Actually, we probably won't even get through all 3 next time. So let's end it here. Remember, guys. Let me see. Questions, cover those answers up, do it before you even have a chance to read them. Discipline yourself, force, and I'm saying this because I am guilty as anyone of kind of sneaking a peek, and then it's confirmation, but what it really is, it's confirmation bias. You're saying, oh yeah, I knew that. No, if you had to peek, you didn't truly know it. So cover up those answers, do each one of these questions. Let me know if you have questions. In fact, what I'm going to do, I believe it is in course tools. I'm pretty sure it's in course tools in Blackboard. You can find and you've probably already used it, a setting for discussion boards. Tell me if I'm wrong, because the student portal, the student interface is not the same as the instructor. I'll go ahead and I'll start a discussion board. You could ask questions on the discussion board. If you want to be even more anonymous, you could text me questions or email me questions. Is this a question right now? You know, Brianna, what the hell are you even doing here?
I need help too.
Breeze from the previous class. Good thing I didn't say anything bad about them. Yes, she is my rock and tells me when I'm still recording stuff that I don't need to be recording. So I will end recording because we don't need